Well, we have discussed before the issue of relying on forests for storing carbon, and there's been a lot of debate about it, because somebody proposed that we can plant 1 trillion trees and solve the climate problem. There is no such silver bullet, of course. Plus, there's been a lot of debate about how the carbon storage even works. Amazon, for example, has been perturbed. I'm struggling with my foot, which is sprained. Amazon is struggling, and now there are some arguments that it's become a carbon source instead of a sink because of all the deforestation, logging, and other perturbations. And of course, wildfires in the last 2 years, especially 23, 24, have shown just how quickly all that carbon can be put out back into the air. So this idea of the paper here is to actually see where, oh, I lost my, where the carbon pools have grown. Is it in the greenery, living trees and vegetation, or is it in non-living pools? Okay, so this is a perspective article on the article that we will look at both briefly. Living and non-living organic matter in terrestrial ecosystems are crucial for the management of global carbon sequestration. So you can think of these as nature-based solution or natural carbon sinks, enhancing sinks at least. Looking beyond the trees for carbon storage, non-living organic matter could create more stable carbon reservoirs. About 1/3 of the carbon dioxide emitted by human activities is absorbed by the terrestrial ecosystems. About 25% goes into the ocean, and the rest tends to accumulate in the atmosphere, of course. These carbon sinks, along with the ocean's slow, how much did we say here? 1/3, yeah. So these carbon sinks, along with the oceans, slow the carbon of atmospheric CO2 and the pace of global warming. The locations where the absorbed emissions are stored govern the long-term stability and management of carbon pools, those places in Earth's biosphere that can accumulate, store, and release carbon. So ocean can keep it away for a long time, but with warming, solubility goes down, biology is being affected, so biological pump and sequestration are being affected. With warming, soil respiration goes up, so it's a very complicated problem. Nonetheless, how carbon is dispersed across different pools on land remains unclear. On page 1291 of this issue, Baron et al., we will look at that briefly, report an unexpectedly large distribution of terrestrial carbon in pools of non-living organic matter that are natural or human-made. We are not calling them abiotic, we are calling them non-living. Carbon sequestration beyond the more vulnerable components such as trees could imply greater carbon stability on land than previously thought. This finding highlights the growing complexity of the future evolution and management of carbon sinks and reservoirs. The primary driver of the terrestrial carbon sink is the rising concentration of atmospheric CO2 caused by, of course, an increased carbon uptake by vegetation through photosynthesis. This has led to a tripling of land carbon sink over the past 6 decades, a tripling of land carbon sinks. However, anthropogenic climate changes, particularly warming, are estimated to have reduced the terrestrial sinks by 27% every year over the past decade. So the warming is accelerating. Maybe we have had 2 big El Niños, but this paper came before the 23-24 warming and El Niño, etc. The single largest decline of terrestrial carbon sinks in the past 2 decades was observed in 2023, so that's covered here already. Although carbon sinks on land tend to have a large year-to-year variability, this record drop underscores the growing sensitivity of carbon sinks and reservoirs to changes in climate and severe weather. The major causes of increased vulnerability of terrestrial carbon sinks include heat waves, droughts, wildfires. Boreal wildfires reached a tipping point early in the past decade when extreme droughts stoked an exponential increase in fire emissions. This culminated in an unprecedented surge of CO2 emissions in Siberia in 2021 and Canada in 2023. A combination of natural disasters is also responsible for turning some regional carbon sinks into sources of emissions. For example, burning of trees in the Amazon forest turned this living carbon sink into a major source of CO2. In addition, deforestation and ecosystem degradation, such as logging, continue to contribute to the net loss of terrestrial carbon to the atmosphere. So that's the story. So the paper analyzed global observational data on changes in the terrestrial carbon pool and report that only 3% of the carbon sequestered over the past 3 decades stayed in living biomass such as tree trunks and leaves. The rest of the carbon drifted as non-living organic matter in other parts of the natural and human environment, such as components in soils, deadwood, and river dams. So dams store a lot of water and you build up carbon behind them as well as you store water. There is also issues of methane emission from there and so on, but nonetheless these non-living carbon pools could be less vulnerable to interferences such as wildfires, droughts, and heat waves compared with carbon stored in a living matter, resulting in a longer residence time and more stable carbon pools than previously assumed. So you have to remember these are all estimates, and then they compare the results to dynamic global vegetation model results as well, as we'll see one table. I won't go into those details, but it's just a matter of estimating and getting some kind of a verification, validation to make sure that the estimates are reasonable, at least for claiming that living biomass and non-living biomasses are growing, but most of the growth is happening in non-living biomass, and dynamic vegetation models may help separate these, or they may overestimate living biomass. Specifically, the paper found that the largest amount of carbon is stored in soils and deadwood. Other non-living components such as harvested wood used for building houses and furniture. So you harvest wood means it captures carbon, you cut it off and you use it for something, so it's locked in, right, sequestered for some time. Also wetlands, lake beds, river dams and landfills, they account for up to 20% of the changes in carbon stocks, the total amount of carbon in a specific ecosystem at a given time. So that's carbon stock. These findings are in complete contrast to a computational analysis that estimated that 70% of the land sink is accumulated in the living components of the landscape in accumulated in living components of the landscape such as trees. Previous ecosystem scale CO2 experiments suggested that possibility of increased carbon uptake by trees without a net gain in carbon, which means planting trees may not be close to being may not even be close to being a silver bullet. The results of the paper provide evidence of the importance of non-living organic matter in carbon sequestration. These are, seemingly details, but they matter, because if we keep on dreaming of planting trees to save the world, then we better be careful, because you may be able to grow them and maybe convert them artificially into dead wood or soil carbon, right? Although non-living terrestrial carbon pools may be less vulnerable to natural disturbances, the replenishment and expansion of storage still depend on inputs from living biomass. Thus, they can also be indirectly affected by the same environmental disruptions as living carbon pools. In addition, human interventions such as changes in the management of wetlands, freshwater reservoirs and rivers, as well as landfills, can influence non-living carbon pools. The broad distribution of carbon in natural and human-made infrastructures paints a more complex picture of drivers that need to be managed to protect and enhance present and future carbon sinks and stocks. I have discussed also the idea of using wood for high-rises, and China is already doing that. You can make them fireproof, fire resistant, at least with some coatings, and you can lock up a fair bit of carbon that way as well, especially since cement production, steel production and concrete are such heavy emitters of greenhouse gases, plus buildings are built for a few decades, then they have to be brought down and rebuilt, new ones are built. So all that concrete is not recycled so efficiently. So I've also discussed recycling concrete elsewhere. So all these carbon sequestration things are related. I'm getting a phone call. Okay, that was an important call. I'm leaving for a hike in the Himalayas next week, but right now I'm sitting with, recovering from an ankle sprain, so I better be ready. And this call is about that. Anyway, um, so we are basically looking at how non-living carbon is adding up and what it means in the end. So if we assume that they are less vulnerable than the trees, as we know by all the wildfires that are increasing in area, maybe not number but intensity, which is a measure of certain things, then all the stored carbon can go kaput. But if we find a way to replenish non-living carbon, then it could be very useful. So reducing uncertainty in the size of living and non-living organic carbon pools remains a priority for carbon and climate projections. Upcoming satellite biomass missions will provide new opportunities to improve estimates of the state of forests and their living carbon pools. Moreover, airborne hyperspectral imagery will allow the tracking of changes in dissolved carbon in inland and coastal waters. Beyond direct measurements, computational models that simulate complex biochemical interactions in terrestrial ecosystems should be expanded beyond the plant-soil system into the freshwater and human environments. So essentially, if you are going to use this as a way of enhancing carbon sequestration in non-living material, non-living carbon pools, then you want also a way of monitoring them as offsets or additional carbon. Let's say a country says we will bury carbon in non-living carbon pools as a part of our nationally determined contributions, then that has to be quantified, monitored, verified, and reported, right? So those are also the issues to worry about. In addition, there is a need to represent missing processes that affect the strength and stability of the carbon sinks and pools of living and non-living organic matter, such as wildfires, soil microbial processes, climate effects, and rate of ecosystem collapse and recovery. Large-scale field observations and computational models need to extend to coastal ecosystems and continental shelves to cover the entire land-to-ocean aquatic continuum and close the carbon sequestration loop. Blue carbon is being touted as another way, and there has been also some ideas put out by Zhang Ning from University of Maryland, my colleague and friend, saying that we can just grow forests and bury them, okay, carbon burial. And he argues that this will be a potential way of storing carbon as well. So although the paper primarily focuses on woody biomass because of its large carbon stocks, the role of grassland dominated ecosystems where soil carbon sequestration is the dominant storage mechanism merits further investigation. A more regional and ecosystem based analysis will further provide key insights to enable the design of strategies for the conservation of carbon stocks and enhancement of CO2 sinks for climate mitigation. So that's the perspective, and we basically got the idea. Now let's look at a few more specific things from the paper itself. It says recent gains in global terrestrial carbon stocks are mostly stored in non-living pools. So this comes down to estimating these and comparing to dynamic vegetation model estimates. As we will see, terrestrial sequestration of carbon has mitigated about 30% of anthropogenic carbon emissions. However, its distribution across different pools, live or dead, biomass and soil and sedimentary organic carbon remains uncertain. Analyzing global observational data sets of changes in terrestrial carbon pools, we found that 35 plus minus 14 gigatons of carbon have been sequestered in land between 1992 and 2019, whereas live biomass changed by 1 plus minus 7 gigaton carbon. So you can see the massive uncertainties in here in these numbers, but this is what we have to deal with, and it's a very non-homogeneous distribution. So global numbers also differ in terms of the life cycle of that carbon pool. In cold climates, it may stay longer than in warm climates, wetter climates, for example. Global vegetation models instead imply that sequestration has been mostly in live biomass. We identify key processes not included in most models that can explain this discrepancy. Most terrestrial carbon gains are sequestered as non-living matter and thus are more persistent than previously appreciated, with a substantial fraction linked to human activities such as river damming, wood harvesting, and garbage disposal in landfills. So I'm not going to go into details of the methodological differences between these estimates and what the dynamic vegetation models do, but you should follow up if that's of interest. But basically, you see here cumulative change in carbon stocks since 1990 to 2020. The study period started here, and carbon change in land carbon stocks is quite impressive with a large uncertainty, as we said, but change in biomass stock is not that impressive. There was a loss and then it has come back to neutral basically in terms of cumulative. So it has become a neutral. It used to be a source and so on, but global vegetation models show reasonably good increase in carbon stocks, but they put it all in biomass, okay, which this paper argues is actually wrong, and there are reasons why models do that, but in the discussion we'll just touch on it. Mean annual rate of change in total carbon stocks and in living biomass over over 3 time periods from our analysis and from dynamic global vegetation models. I am not going at all into those details. Annual change in total carbon on land, gigaton carbon per year. Annual change in living biomass carbon in gigatons per year. Current study, so they are looking at different periods, 1993 to 2000, 2000 to 2010, 2010s, and the total period. And you can see there is an increase, 0.8, 1.3, 1.7 for a total of 1.3 because of the way things work in okay, so you don't just add up these numbers to get the total. There are reasons why that happens. On the other hand, models say 1.2, 1.2, 1.6, and the total number is still similar, but the pools are very different. Oftentimes models do better when they know the answer. This is always tricky. I won't go more into that, but if you want to be cynical about models, that's the way you would think about it. Annual changes in living biomass. The current study says there were negative numbers, so that's why this total is not the sum of these. And 0.2 and 0.4, so you can see relatively small part, and total change is only 0.02 with the uncertainty of plus minus 0.3, 1 order of magnitude larger, whereas models say it's been positive all the time and is actually overall positive 0.8 gigaton carbon per year. These look like small numbers, but actually considering the area and how much we are emitting, these are significant numbers, especially in terms of the differences between what this estimate says and what the models say. So I will just jump directly to the discussion. I am not going into details because I'm just interested in highlighting these differences. Our analysis revealed that while land accumulated about 35 plus minus 14 gigatons carbon during the study period, global live biomass stocks increased by only 1 plus minus 7 gigaton carbon. Most terrestrial organic carbon gains appear to be sequestered in non-living matter. This result might seem surprising given that a key mechanism for the increased uptake of CO2 by land is increased plant productivity due to CO2 fertilization and or forest regrowth. There is also afforestation efforts and so on, and they are all linked to plant growth. Nevertheless, our results are consistent with the results of prior studies as well as with independent data on changes in non-living carbon pools, as we discussed below, which I'm going to jump to the end. Our analysis also suggests that carbon sequestered on land is stored for the most part in pools with residence times longer than those of living biomass, such as soil organic carbon has approximately 5 times longer residence times than living biomass, and thus could be more persistent than previously appreciated. At the same time, a large fraction of the carbon is likely stored in pools that are tightly linked to human activities, which implies that policies regulating such pools through waste management or dam removal could affect the carbon cycle in measurable ways, and that there are hard limits to the capacity of some of these pools. For example, there are a finite number of rivers to dam. As such, these results can inform future climate change mitigation efforts. Of course, rivers have lots of other problems, and a lot of people hate dams. I mean, dam building has got many problems. Methane emission is one thing, but the cycles of loading and unloading them are also, argued to have produce earthquakes, and of course biodiversity impacts, because fish lose the continuity if there is a big dam, and salmon problems in the US has become a showpiece for that, and so on. So I'm going to leave it here, but just remember that there is growing land carbon, but it is all coming in non-living carbon pool and not the living biomass. Okay, so let's leave it here.